Hi everyone, it's Michael. So I have another fantastic AIME problem for you all. So for those of you that haven't heard, the AIME is the exam used in the US to see who qualifies for the USA Math Olympiad. And all the problems have answers from 0 to 999, so they're all integers, but they can all be quite tricky. So if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So we have two circles that intersect in points X and Y. We have a common tangent to those two circles, and it touches them at points A and B. And then we draw a circle through A and B, and it cuts the two circles at points C and D, and it does so in such a way that C, Y, and D are collinear. And then we're given that XC is 67, XY is 47, and XD is 37. And the problem asks to find AB squared. So I wanted to note that I haven't drawn the diagram to scale. So as you can see in the figure, it kind of looks like XY is less than XD, but actually XY is 47 and XD is 37. So even though I didn't draw the diagram correctly to scale, the logic I'm going to use to get to the final answer will still be correct. And the reason why I didn't draw the diagram exactly according to the numbers is because if I did, it doesn't look very nice. The points are very bunched up. All right, so how do we get started here? So the first thing I noticed is that there's three circles, and so we can apply the radical axis theorem. And so the three radical axes are AD, XY, and BC, and so they have to concur at a point. So here I'm just writing that I'm using the radical axis theorem. So I'm going to draw those three lines, AD, XY, and BC, and they all have to meet at a point F. So when I first solved this problem, I wasn't 100% sure this would be useful, but after playing around with it a little bit, it turns out that it is quite useful. Because now, if you look carefully, we can apply Mikelle's theorem. So if you look at the triangle FDC, and you look at the 3 points on it, A, Y, and B, Mikelle's theorem says that the circles through DAY, BYC, and FAB have to concur, and so therefore they'd have to concur at the point X. So said another way, that means FAXB is cyclic by Mikelle's theorem. So I'm just going to do a short proof of Mikelle's theorem for those of you that haven't seen me use it on my channel. But it's also not hard to use an angle chase to prove that FAXB is cyclic. So I'm going to do that right now. So we have angle, so before I draw on the circle, angle AXB, that's 360 minus angle AXY minus angle BXY. And we can rewrite that as 180 minus AXY plus 180 minus BXY. And then since these two quadrilaterals are cyclic, that's the same as angle ADY plus angle BCY. But those are two of the three angles in triangle FDC. So that's 180 minus the third angle, which is angle AFB. And so since AXB is 180 minus angle AFB, then that's how you prove that FAXB is a cyclic quadrilateral. So I'm going to draw on that circle. All right. The next thing I notice is that whenever you have a common tangent to two circles, so AB in this case, the radical axis XY has to bisect AB. So I've mentioned this on my channel before, but I'm going to give a quick proof using power of a point. It's not too hard, so I'm going to let G be the intersection of XY with AB. And then by power of a point, we have GA squared as GX times GY, since GA is tangent. And we also have GB squared as GX times GY. And so that means that GA has to equal GB. All right. And not only that, I'm going to use another power of a point argument to show that GF is equal to GY. So it's fairly straightforward. We have GX times GF is equal to GA times GB by power of a point. But GA times GB, that's the same as GA squared from the above line, and GA squared is GX times GY. So if we have gx times gf is gx times gf, gx times gf is equal to gx times gy, then gf is equal to gy. So we're getting a lot of useful information here. G is the midpoint of Fy. All right. Now the next part, I kind of just played around with angles, and I found that triangle FXD and triangle CXF are similar. So I feel like maybe I got a little lucky here, but I'm going to show you the angle chase that ends up proving that. So we have angle XDF is equal to angle XDA, which is equal to angle XAB, since AB is tangent to the circle. And angle XAB is equal to angle XFB, which is angle XF. This should be XFC right here. So we have angle XDF is equal to angle XFC, and then we can make the same argument to show that angle XCF is equal to angle XFD. And so that means that those two triangles have to be similar. And that ends up being very useful. So triangle XDF has to be similar to triangle XFC, since two of the three angles are equal. And from there we can use ratios. So we have dx over xf has to equal xf over cx. So I'm going to write out these ratios. Dx over xf is equal to xf over cx, because these are corresponding pairs of sides in those two triangles. And then if you work out the algebra, that means x squared has to equal, or that means xf has to equal the square root of dx times cx. And now we can start substituting the information. So xf, it turns out, is the square root of 37 times 67. All right. And if we know xf, then we know fy. That's just xf plus 47. So I'm going to write that out. Fy is 47 plus the square root of 37 times 67. And I mentioned before that g is the midpoint of fy. And so from there we can get gy. So gf and gy are both half of fy, which is half of 47 plus root 37 times 67. All right. And now we're just about there. So AB squared, we know that g is the midpoint of AB, so that's the same as 2AG squared. So I'm going to write this out. So AB squared, it's 2GA squared. And then if you distribute, so the parentheses should be, the squared should be outside the parentheses here. But if you distribute the squared, that's the same as 4GA squared. And GA squared is GX times GY, so that's 4GX times GY. And we know GY from above, and GX is GY minus 47. So this is 4 times GY minus 47 times GY. And if you work out the algebra, the square roots start to cancel nicely. You end up with just AB squared is 37 times 67 minus 47 squared, which is 270. So I really like this problem. I like how it used Mikelle's theorem and the radical axis theorem. But there were also a couple of other solutions. So if you want to check them out, click the link on the Art of Problem Solving forum in the description of my video. So if you like this, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.